In this lecture, we'll study adjunction, which is perhaps the most important construction that comes from category theory. I'll start with an example which seems to have nothing to do with category theory, which is the definition of a free group. So recall free groups. You can look at week 3 of Algebra 1. And how it works is this. So let A be any set and a group word in A I'm using the phrase group word because if I just use words, I'll get what is called the free monoid, but I want to construct the free group. So a group word in A is an expression of the form W equals A1 to the power N1, A2 to the power N2, AL to the power NL, where L is any non-negative integer. I allow L to be 0, in which case I'll be looking at the empty word, where each AI comes from the set A, and Ni is an integer. Okay, and a reduction of a word say as above is one of the following steps. So what you do is you can delete a term of the form AI to the A to the power 0. Because you can, if any of the exponents in this W is 0, you can just delete that term. And the second one is you can replace A to the N1 and A to the M by A to the N plus M for any A in A. So this is for all A in A, and this is for all A in A, M, N in Z. So basically what we're saying is if two consecutive terms in your word have the same letter, then you can club them and replace the exponent by the sum of the two exponents. So these could be positive or negative, but you add them up as integers. Okay, so this is called reduction, and note that each time you reduce a word, you will be reducing L itself. You are reducing the number of terms in the word. And so this reduction process will eventually stop, and so every word can be reduced till it can no longer be reduced any further. Maybe you'll get the empty word, but certainly you'll reach a stage when you cannot reduce it any further. So a reduced word is a word that cannot be reduced any further. And now the free group of A is defined as follows. Its elements are reduced group words in A, and its multiplication operation is a concatenation of words followed by reduction. So if you have two words, a1 to the power n1, a2 to the power n2, al to the power nl, and say you have another word b1 to the power m1, k to the power mk, then their concatenation is this word a1 power n1, al power nl, b1 power m1, bk power mk. Now this word, this concatenated word may not be reduced. It could be, for example, that al and b1 are equal, in which case you would have to club these two terms to get a reduction. And after you club them, it could happen that m1 is minus nl, in which case those things cancel out and so on. So you may have to do a series of reductions, but at the end of the day you'll get a reduced word, and that will be that will be an element of the free group on A, and so that will be the product of these two words. And you can check, it's not very difficult to check that this is actually gives rise to a group. These things are done maybe in a slightly less generality in Algebra 1. This is also related when we studied co-product in the category of groups. So it turns out that free group on A is actually A in A. So this is just integers, one copy for each A. This is a direct sum in the category of groups. How does this work? So we saw finite direct subs. It was what we called an amalgamated product. So let iota from A to free groups on A be the function. So the free group on A be the function which takes A to A, where this is to be thought of as the one letter word. Consisting of just one letter, namely A. Now suppose H is any group and F from A to H is any function, then we can define F hash from the free group generated by A to H as follows. So I need to define F hash on every reduced word. So A1 to the N1, AL to the NL will be, so now F is just a function, so I have F of A1, that's an element of H, and I'll raise it to the power N1, F AL to the NL. And it turns out that F hash is the unique group homomorphism from the free group on A to H, such that the diagram, so let me draw this diagram. We have A, we have so let me just do a slight suggestive change of notation here. Let me call this, instead of iota, let me call this eta subscript A. You'll see that it is a natural transformation. So we have A, eta subscript A to free group of A. And then we have any function F from A to H, any group. And what we are saying is that there exists a unique group homomorphism f hash from free groups of A to H. Okay, so this is a universal property of the free group on A. Viewed in another way, we have that set homomorphisms or arrows in the category of sets from A to omega H is the same as group arrows from free A to H, where omega denotes the forgetful functor from the category of groups to the category of sets. Now this kind of situation is known as adjunction. So what we say is that FR is a left adjoint to omega, or we may say that omega is a right adjoint to FR, or we may say that FR comma omega is an adjoint pair of functors. Okay, so here note that FR occurs on the left and omega occurs on the right, and you're allowed to go for A morphisms from A to omega H. This was what we called F, and arrows from free A to H. This is what we called F sharp, and this was a bijective correspondence. So let me make this idea of adjunction more precise. So the situation is as follows. Suppose C and D are two categories. And you have functors f from C to D and g from D to C. Functors. Then we shall say that f comma g is an adjoint pair or as I explained before, we would say that f is a left adjoint of g, or we could say that g is a right adjoint of f if there exists a natural transformation eta from the identity functor from C to C to the functor G circle F. So both these are functors from C to C such that for every object A of C and every object B of D, and for every arrow F in the category C from A to G of P, we have there exists a unique arrow F sharp in the category D, and now we would have FA to B, such that the diagram, so we have A and then we have G circle F of A, and from this object to this object in C we have the arrow eta A coming from the natural transformation eta, and given F from A to G of B, we are saying that there exists unique F sharp such that if you put G of F sharp here, not F sharp itself, but if you put G of F sharp here, then this diagram commutes. This sets up a bijection. I should say there exists a unique F sharp. So the uniqueness is also required. So this sets up a bijection between F and F sharp because F sharp exists uniquely if F is given. And so that's a function in one direction. In the other direction, given F sharp, you can take G of F sharp and compose it with eta A. And so you get F. And so what this is saying is, so this is completes the definition, but what this is saying is, we have in the category C, the arrows from A to GB are in bijection with the category D, the arrows from FA to B. In our example, we had taken C to be the category of sets, D to be the category of groups. We had taken F to be the free group functor. This is from sets. Given a set, it associates a free group to it. G was the forgetful functor from group to set. And eta is a natural transformation from the identity functor from the category set to itself to the functor G circle F. And what is this? So given a set A, this eta A goes from this to omega of free of A. In other words, eta A is just a function of sets, like a function with no further requirements about being a homomorphism or anything, from A to the set underlying the free group generated by A. So it's just a function from A to FRA. And the universal property for the free group is exactly the statement that F, R, and omega form an adjoint pair. Now, the notion of adjunction is very useful. We will see later in this course that suppose you're given a ring R. So example application, which you'll see in detail later in this course. So let R be any ring, and let M be a right R module. So that means there's a function from M cross R to R satisfying various conditions, in particular M, R. So this is usually denoted M comma R goes to MR, and MRS is MRS, among other conditions. So, so we're saying that M is a right R module, and let's consider the category of left R modules. Now there's a functor, I'll call it hom M comma dash. This is a functor from the category of abelian groups. So this is the category of abelian groups to the category of R modules, left R modules, which does the following. It takes an abelian group A and maps it to group homomorphisms from M to A. So if you have phi belongs to hom MA, you can think of phi, define R phi to be, so for every R in the ring R, you can define R phi of M to be phi of MR for all M in M, R in R. And this makes HOM MA an R module. So in this way, a HOM M dash defines a functor from the category of abelian groups to the category of left R modules. You still need to think what it does at the level of arrows, but here's what it does at the level of objects. And this functor has a left adjoint. And that's a functor called tensor with M over R. This is a functor from the category of R modules to the category of abelian groups. And what it does is it takes an R module N and maps it to the abelian group M tensor over R N. This will be explained later in the course. And so the adjunction here says that the arrows in the category of abelian groups from M tensor N to any abelian group A is the arrows in the category of R modules from N to HOM MA. And you can, well, if you know a little bit about tensors, what it does here, if you have phi here and psi here, then they are related by the following equations. Psi of n of m, maybe I'll write psi on the right, phi of m tensor n is equal to psi of n of m. So you can use this identity to define phi in terms of psi and psi in terms of phi.